Yeah, so I'll start with the session. I'll continue with the session. So, basics of is the screen visible? One second. Yeah, hope the screen is visible. Is the screen visible?
Yeah, it's visible.
I'll start with the basics of Boolean algebra. So, yeah. So, what is Boolean algebra? So, see this in this meme, you can see that algebra says 1 plus 1 is equal to 2, binary says 1 plus 1 is equal to 1, 0, Boolean algebra says 1 plus 1 is equal to 1. So, this is how what Boolean algebra is. You can say that Boolean algebra was first Boolean algebra was developed by George Boole in 1954. So, if you say if what is Boolean algebra, it's a system of algebra with operate with numbers and operators with unapproved axiom and postulates. So like for now we have to assume ones and zeros as on and off, and we have to understand how it works. So 1 plus 1 has we have to you have to recognize 1 and 1 as like two switches which are on. So if or if one or one is will be represented as two switches in series. So if you on both the switches, it's just the same as the current will pass, so it's just one. So if two switches are on, it represents on, like 1 plus 1 is equal to 1. That's what it means. So this is what Boolean algebra is. We have to consider every ones and zeros as on and off, and we have to calculate the algebra of it. So yeah. So why Boolean algebra? So Boolean algebra is a mathematical method actually that simplifies circuits very easily. So when we have very complex circuits and things, we'll be using this Boolean algebra. We Boolean algebra simplifies everything of it. So we'll have a set of properties, and we can make complex problems easier in Boolean algebra. So yeah. So two valid Boolean algebra. So two valid Boolean algebra is like two numerants with operator in between. So as in the image you can see, or operator like plus 1 plus plus 1 1 plus 1 1 plus 0 can be represented as switches in series. So we can say that if A or B can be represented as two switches in series. So if either A, if if just one switch is pressed, if just A is pressed, still the circuit is incomplete, right? So both if sorry A and B will be represented as switches in series. So if just A is pressed or just B is pressed, the circuit is incomplete. Both A and B should be pressed in order for the circuit to be completed. So A and B should be pressed for the circuit to be complete. uh, yeah. So yeah, when so this is what and operator, and that is multiplying operator means. So in Boolean algebra we have two operators, one plus and multiplication. Plus represented the or operator, and dot operator represents the multiplication, that is the and operator. So and is, we have to imagine and as two switches in series, and or operator has two switches in parallel. So if either A is pressed, if just A is pressed, the circuit becomes complete, right? So either A or B or both should be pressed for the circuit to be completed. So this represents the or operator, A plus B. So if you see that 0 plus 0 is equal to 0, so if both the switches are not pressed, so 0 plus 0 gives 0, so the circuit is incomplete. 0 plus 1, so if any of the switches pressed, so say A is pressed or B is pressed, the circuit will be complete. So 0 plus 1 or 1 plus 0. So if A is pressed or B is pressed, it's going to be same. So this means that it follows commutative property. So 0 plus 1 is equal to 1 plus 0. And then coming here, 1 into 1 is equal to 1. So here A and B. So A and B, if it's pressed, it gives 1. So the circuit is complete. That's what 1 into 1 is equal to 1 means. So and then moving on, 1 dot 0 is equal to 0 dot 1. If we can say that either A is pressed or just B is pressed, the circuit is incomplete, right? So either if only A or only B, if anything happens anyway, the current won't flow and the result will be 0. So 1 into 0 is equal to 0 into 1 is equal to 0. So this is what commutative property in AND gate. So and then it also follows the distributive property. Yeah. See, we can say that x into y plus z. So x, if when we have an AND gate with one input as x and the other input as y plus z. What is y plus z? Y and z are put into an OR gate and then the output is put into one input of the AND gate with another input as x. So you can imagine as a set of um, logic gates, and then which it can be represented as xy plus xz, just multiplying it inside the brackets. So this follows the distributive law as well. So there are a set of properties which can be done inside this Boolean algebra, like the identity x plus 0 is equal to x, x into 1 is equal to x. So like we have to imagine it as an OR gate, and one input is 0 and the other input is x. So whatever the input is, the OR gate will give the same input, right? So this is how we have to think of this whole table. There are many properties with x plus x dash is equal to 1. So what you can do is you can use logism and try out each and every properties on your own. So you can take this as your maybe task and try it on your own. So this will give you a strong grip in the logism and help you formulate much more circuits. And then so these are the formulas, and the one of the important formula is the De Morgan theorem. So De Morgan theorem says that um, um, x plus y the whole x plus y the whole complement y complement. So if we put an OR gate between x and y and then complement it, we'll get a AND gate of x complement and y complement. This is a De Morgan theorem. The same way we can say that and the so it's just put an OR gate, put an NOT gate after the OR gate is same as putting a NOT gate first and then putting an AND gate. This is how this is we can say represent this. And the same way, instead of plus like if we have AND gate, the whole complement, if it is complemented, we'll get x complement plus y complement. This is what we'll get. This is the De Morgan's theorem, which is a very important theorem we'll be covering later. So moving on, Boolean functions. So this will be taken up by Santosh SP. Yeah, over to Santosh. Is this fine? Is there any doubts? You can put the doubts in the chat box.
Yes, okay, moving on. I will now we'll talk about Boolean functions. Can I move to the next page, please? I'll present. Yes.
Yeah.
I hope my screen is visible. The slides are visible.
Yeah,
Okay,
it is.
so now we'll talk about Boolean functions. We'll first talk what's a Boolean. Boolean function is basically an algebraic expression that has binary variables, constants, and logic operations involved. So it's basically same as a mathematical function, but instead of the normal math variables, we have these binary variables which can only take 0 or 1. And instead of mathematical operations, we have binary operations, binary logic operations like and or and complement. For example, we consider this function f equals x plus y dash c. So in this function, there are three input variables here. X, y, and z are the input variables. So these are related by specific logical operations. Like you can see an OR symbol over here. We can see y is complemented. So we do some certain logical operations to these input symbols to generate an output, which we call here as a function. So in this function, x, y, z are the inputs, and f is the output of the function. Okay, now we'll see what's a truth table. So as you have seen, truth table in the discussion of logic gates, where we do logic gates for where we do truth tables for every logic gate. So truth table is just a table which has all different possibilities of inputs along with different outputs it produces. So let's consider the function f equals x plus y. So our, as x and y are binary variables, it can either take 0 or 1 and y can either take 0 or 1. So we have 2 times 2, total four possibilities in total. So we have 4 entries in truth table. So we'll first put a column x, we'll next put a column y, and next we'll put x plus y. So we'll write 0, 0, 0, 1, 1, 0, and 1 to account for all 4 possibilities, all 4 input possibilities, and x plus y is the output possibility. So this is the same as the OR gate which we have seen before. So when both of these inputs are 0, the output is 0, and whenever either of the inputs is 1 or both of these inputs are 1, the output is 1. So this is the truth table of the OR gate, or you can see the truth table of a function f equals x plus y. So moving on, we'll consider another function f equals x plus y dash z. We'll learn how to write truth table of this function. So there are 3 variables over here, 3 binary variables which can either take 0 or 1. So as there are 3 variables, there are 8 possibilities in total. So there are 8 entries for the truth table, which we can start writing from 0, 0, 0, 0, 0, 1, 0, 1, 0 up to all 1, 1, 1. So the fourth column is y dash, which is the exact complement of the y column. So we just invert the entries of the y column to create the y dash column. So as you can see in the first row of the y column, we see 0, we see a 1 in the y dash. We see 0 zeros first, we see 1 ones. We then see in the third and fourth rows of the y column, we see 2 ones. But in the third and fourth rows of the y dash column, we see 2 zeros. So a y dash column can be produced by directly inverting the outputs of the y column. And similarly, if we put an AND operation between the y dash and z columns, we can get the fifth column, which is y dash and z. So from the third and fourth column, if you see the first row, we get 0 and 1. 0 and 1 is 0. 1 and 1 is 1. 0 and 0 is 0. 1 and 0 is 0. And similarly, we can write the whole column of we write the whole truth table for y dash z. So finally, the function which we require is x plus y dash z. So finally, if we consider an OR operation between the column 1, which contains x, and the column 5, which contains y dash z, we get the required function. So as you can see from the first row of the x column, we have 0, and the first row of the fifth column, we have 0. So 0 or 0 is 0. So in the second row, we can see that we have 0 in the x, and we have 1 in the y dash z column. So 0 or 1 is 1. And similarly, we can look at each of these entries. We can write the truth table for f equals x plus y dash z. Okay, now we'll learn now we'll learn like if they give you a logic circuit, with inputs, how do we find the boolean function that it represents? So we'll take an example first. If we consider the circuit given here, we have like 2 AND gates, we have 2 NOT gates, and then a final OR gate which outputs the function f. We have 3 inputs x, y, and z. We have 3 inputs x, y, and z. So to find the Boolean function which this logic circuit represents, we can just navigate. We can just navigate from the input along the lines through the gates to the final output. So if we navigate from the input y to the input of the AND gate, we can see that it passes through a NOT gate. So the input y gets inverted, and we get y dash over here. And the input x stays as such, and the input of the AND gate is x and y dash. So this is an AND gate, so the output it produces is x, y dash, which goes to the input of the OR gate. Now, I'm considering the other AND gate. We have z, which is directly passed to the input of the AND gate, so it stays as such. But x over here, it passes through another NOT gate. So the input x gets inverted to x dash, and the inputs of the AND gate is x dash and z. So the output of the AND gate, it just multiplies both of these binary variables. We get x dash times z, x dash z. So the final OR gate, it gets both of these, the inputs which the final OR gate gets, it's x, y dash and x dash z. So the final output represented by that is f equals x, y dash plus x dash z. So in a similar way, we can find the Boolean functions which different logic circuits represent. Okay, so it's now time for a quick question. So, do you think when the LED glow, these inputs are one, and this input is zero? You can put your answers in the chat, guys. Okay, so we have quite a bit of responses, and the answer is LED glows. So we connect these inputs 1, 1 and 0 to the circuit. We can see that this whole wire is in high potential. So we can consider both the inputs to the AND gate to be 1, and so it outputs a 1. And now if you travel along this path, uh, it encodes as a NOT gate, so it inverts the input. So the output to the NOT gate is 0. From if we travel from this input, if we travel from this input to the input of the NOR gate, again we get 0. So the output of NOR gate is 1. So if we consider the final AND gate, both these inputs are 1. So its output is also 1. And therefore the LED glows. So most of you have got the answer right. Congrats, guys. So moving on, we'll consider another one example. Let's consider the function f equals x plus y dash plus z dash. Um, we can write its truth table by following the same procedure which we did earlier. We just write these three input columns x, y, and z. We have 8 possibilities in total. So we write all the combinations from 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So z dash column is basically the inverse of the z column. Therefore, all the entries in the z column are inverted. So the z column has 0, 1, 0, 1. So the z dash column has 1, 0, 1, 0. So everything is basically inverted, and you can write it like that. And similarly, we can write the y dash column by inverting all the values in the present in the y column. So if you see the second column, its rows, uh, the inputs, the numbers present in the second column are 0, 0, 1, 1, 0, 0, 1, 1. But in the y dash column, it's 1, 1, 0, 0, 1, 1, 0, 0, which tells us y dash, which can be reduced from the fact that y dash is just the inverse of y. So if we consider the OR operation between x, y dash, and z, I mean the first column, fourth column, and fifth column, we get the final truth table of the function, final truth table of the required function. So if we look at the first row of the first entries of the first, fourth, and fifth column, we can see that it has a 0, it has a 1, and it has a 1. So if we consider an OR operation between them, 0 plus 1 is 1, and 1 plus 1 is just 1. So the output present in the first entry is 1. If we consider the second entry, the input is 0, 0, and 1. So 0 plus 0 is 0, and 0 plus 1 is 1. So the output is 1. And similarly, if we do the same thing for every entry in the truth table, we can get the truth table for the required function, which is f equals f plus y dash plus e dash. Okay, so now we'll talk about how to represent this as a logic circuit. So here we can see we have a three input OR gate. From the function, we can see that we are clearly dealing with the complements of y and z. We are not dealing with y's and z's. We are dealing with y dash and z dash. So we use two NOR gates to invert y and z to get y dash and z dash, and we feed x, y dash, and z dash to an OR gate, to a three input OR gate, which outputs the function f equals x plus y dash plus z dash. So now moving on, we'll learn how to use the De Morgan's theorems to find the complement of a function. So the complement of a function is we can consider it just like the inverse of the function. As I learned, a NOT gate inverts the input to a given output. So whenever the input is 0, the output is 1. Whenever the input is 1, the output is 0. In a similar way, the complement of a function is basically its inverse. Whenever in the truth table, the function has zeros in its entries, we invert them, and its complement has ones in those places. And whenever it has ones, its complement has zeros in those places. So complement of a function is basically the inverse of a function. Okay, to get the complements of functions, we can use the De Morgan's theorems, which Jairam discussed on previous slide. The theorems which we'll be using is x plus y whole complement equals x complement and y complement. So it's like if we have two input variables x and y, if we first consider the OR operation between them and complement the output which we'll get is same as the AND operation between the complements of the individual variables. So the output which we'll get is the same output which we'll get if we consider the AND operation between x dash and y dash. So the second De Morgan theorem, it states that if we consider the complement of x and y, we'll get x dash plus y dash. So this basically means that if we have two input variables x and y, first we consider its AND operation x and y. Now we consider its complement. We get some output. That output is same as considering the OR operation between x dash and y dash. So this is what De Morgan's theorem basically states. Yeah, and now we'll consider the function f equals xy plus z. So by using the De Morgan's theorem, it's pretty simple. We can just uh, use the De Morgan's first theorem to expand the complement over the sum terms. Then we can use De Morgan's theorem again in xy whole dash to give x dash plus y dash times z dash. And on distributing this inside, we get the complement. If we get the complement f dash equals x dash z dash plus y dash z dash. I think we are pretty much done with the slides today. And as we have more time, I'll just do a simulation and logism. We'll just do this function x plus y dash plus z dash. I'll just show you how to make this case using logism as we have some more time. I hope my Logicent screen is visible.
Yeah, it is visible.
Okay. So we'll first take an OR gate. In the inputs, as we are going to use a 3-input OR gate, we'll from the from the left hand side in the properties tab, we can change the number of inputs to 3. We can just click it and edit it. We'll get 3 inputs. As we're going to use a 3-input OR gate, we can change the number of inputs to 3. We can just extend these input pins and the output pins like we did before. From the input output tab in the left side pane, we can add an LED. And now we can start adding the input pins to these input pins to these. So we can first add these. We can first add the input pin corresponding to input X. Now we can we can take a NOT gate from the top corner. We can connect it to the input of the OR gate. And now we'll take two other input pins. We'll add it to the inputs of the NOR gate. So this basically represents the function which we saw before, x plus y dash plus e dash. And now we can change these values. You can see when the input becomes 0 and when it becomes 1. As while you can change when you change these values, you can compare these with the truth table and see that if the truth table is correct or not. So I think we are pretty much done with the presentation. So thanks a lot you guys for attending it. And make sure that you attend the next sessions because it's going to be even more interesting. We'll be building even more bigger and more amazing circuits using logarithm from the next session.
Yeah, so attend all the 5 sessions, guys. So at the end of this week, you will be able to design your own logic circuit. So if you attend all the sessions, you'll be able to understand it. So yeah, that's it. So if you have any doubts, you can put in the chats. We'll be clearing it. Feel free to ask doubts, guys. Okay, thank you for attending, guys. So I'll end the meet. Thank you.